Our goal in this video will be to sketch the graph of a polynomial. And to do this, we'll begin by recapping some of the tools, skills, and concepts that we'll need to do this. First, we can recap end behavior. And the end behavior of a polynomial is essentially asking what happens as x goes to positive infinity and as x goes to negative infinity. How does our function behave? What happens to the values of f of x? Do they go up off to infinity, or do they go down off to negative infinity? And to determine this, we use the leading coefficient test. In other words, depending on whether that leading coefficient an was positive or negative, we would have different cases of end behavior. And additionally, this depended on the parity of the degree. In other words, if we had an odd degree, this behaved one way, versus if we had an even degree, this behaved another way. And again, here, degree is just the largest exponent. And one way that we were able to think about this was comparing them to graphs that we're already familiar with, namely that of x squared, which has an even degree and a positive coefficient, just 1, and that of x cubed, which has an odd degree and a positive coefficient, again just 1, and then their reflections. So if a polynomial has an odd degree and a positive coefficient, it's going to behave at the ends like y is equal to x cubed, which is to say that as we look to the left, it's going to go down to negative infinity, and as we look to the right, it's going to go up to positive infinity. This will be the reverse, or the reflection, if we had a negative coefficient. In other words, as we look to the left, this will go off to positive infinity, and as we look to the right, it will go off to negative infinity. Likewise, we can think about functions that have an even degree, kind of like the behavior of x squared. Again, at least at the ends. So in the case of a positive coefficient and an even degree, this behaves like the function x squared at its ends, and so it will go off to positive infinity as we look to the left, and positive infinity as well as we look to the right. And once again, making that coefficient negative will just take the reflection of this. In other words, going off to negative infinity at the ends in both directions. Next, we can think about the zeros, or the x-intercepts, and their multiplicity, and how that multiplicity affects their behavior at the intercepts, at the zeros. First, we know that an intercept, or a zero, occurs whenever f of x is equal to 0. In other words, when we intersect with the y-axis, so when y is equal to 0. And for any of those zeros, for any of those roots, the multiplicity was essentially just how many times is the corresponding factor being multiplied. So is the number of times a zero's corresponding factor is being multiplied. So specifically, if we had a function like p of x equal to x plus 1 cubed times x minus 1 squared, we would say that the root of negative 1, which corresponds with the factor x plus 1, so the root of negative 1 has a multiplicity of 3, because that's the exponent here, and the root of positive 1, which corresponds with the factor x minus 1, has multiplicity of 2, because that corresponds with the exponent here. And in terms of how this reflects on the graph, if we had an even multiplicity, then at our root, our graph would touch and turn back. So we'd see something like this. So it touches and turns back. And when we have an odd multiplicity, the graph of our function would cross through at the x-axis. So here it crosses. We can also sometimes utilize what we know about y-intercepts and symmetry to help us get a picture in our heads of what a polynomial might look like. Specifically, we know that y-intercepts occur when x is equal to 0, and so in order to find them, we can just compute f of 0. Then thinking a little further back, we've discussed two types of symmetry that can also apply to polynomial functions. We called a function even when it's symmetric about the y-axis, which we see, for example, in a function like y is equal to x squared, where f of negative x is the same as f of x. And at least in terms of polynomials, this would occur if all exponents were even. All exponents are even. Or on the other hand, an odd symmetry, which is symmetric about the origin, which we'd see as an example in something like y is equal to x cubed, where f of negative x is equal to negative f of x for all values of x. Or in particular to polynomials, all exponents are odd. All exponents are odd. And finally, we can talk about turning points, which we haven't discussed specifically before, but all we really mean when we say turning point is a point where the function turns around. In other words, maybe it goes from increasing to decreasing or decreasing to increasing. And many of our polynomials will have multiple turning points. And specifically, in the same way that we saw a polynomial of degree n has at most n roots, this is also similar for turning points, just one fewer, right? Because if we had 1, 2, 3, 4 roots here, then in between those 4 roots, we have to have 1, 2, 3 turning points. So again, one fewer. In other words, a polynomial of degree n has at most n minus 1 turning points. And now, utilizing all of that information, we can sketch the graph of a polynomial. So let's sketch the graph of f of x equal to negative 2 times the quantity x plus 1 squared times the quantity x minus 2. The first thing we can do here is explore the end behavior. And to do that, we'll be using the leading coefficient test. Now here, since our function is not fully multiplied, in order to find that leading coefficient, we'll have to multiply all of the first terms here. And so we'll have negative 2 from here times x squared from here times x from here. And multiplying all of those out will give us negative 2x cubed. And so in particular, we have an odd degree and our leading coefficient an is less than 0, it's negative. And so what that tells us is that this will behave a lot like negative x cubed. In other words, as we go to the left, as x goes to negative infinity, our function f of x is going to go up. And as we go to the right, our function f of x is going to go down to negative infinity. And so we can roughly fill that in here to give us a sense of what's going to happen at the ends of our graph. Next, we can find the zeros and their multiplicity. Since our function is already written in factored form, we know that we can find the roots by solving for where each of the factors themselves are equal to 0. In other words, when x plus 1 is equal to 0, or when x minus 2 is equal to 0, giving us x equal to negative 1 when we subtract that 1 from both sides, and x is equal to positive 2 when we add that 2 to both sides. And so if we go ahead and plot those points, we'll have x equal to negative 1 and x-intercept here, and then x equal to positive 2 and x-intercept here. And beyond that, the multiplicity of those roots will tell us the behavior of our function at those points. So first, looking at x plus 1, that's this intercept here. We know that that's being raised to the second power, which is an even multiplicity, so it's going to have to just touch and turn back. And then at x minus 2, we don't have an exponent written there, but that implicitly means 1. And so since that's odd, we'll know that the function, or the graph of the function, crosses at that point. And so we can loosely sketch here this touching versus this crossing. And the reason that I know to start up top here is because to the left we're up top here, versus the reason I know to start down below over here is because we're down below over here. And since our function is continuous, The only way we'd ever be able to make it back up to the other side or back down to the other side would be to cross through the x-axis itself, which would have given us another root to begin with, right? So we know for sure that this can't happen, for instance, because if that were to happen, in order to go off to infinity as we go to the left, this graph would have had to turn around and cross the x-axis again, which would have given us another root when we solved in the first place. Next, we can take a look at the y-intercept. This will give us just one more point to plot to help us connect all of the dots. We know that we can find this by computing f of 0. In other words, -2 times 0 plus 1, the quantity squared, times 0 minus 2. Simplifying this, we have -2 times 1 squared times -2, which is 4 times 1, or in other words, just 4. And so we can go ahead and plot our y-intercept here at 0, 4. And then we have roughly enough information to connect the dots. Now, we could consider symmetry here, but because this has both odd and even exponents, it's not going to be either an even symmetry or an odd symmetry. And so we can go ahead and sketch in the rest of our graph to look something perhaps like this. Hopefully your artistic skills are a little bit better than mine, but this at least gives us the general shape of what this polynomial is going to look like. And finally, as a check, we can consider the turning points. We know that for a degree nth polynomial, we can have at most n minus 1 turning points. And so if we look here, we have a degree 3 polynomial, which means we can have at most 2 turning points, and we can check to make sure we don't exceed that by identifying our turning points here on our graph and seeing that we have only 2. So by putting together all of those pieces, we can then connect the dots to have a general sketch of a polynomial function. And we can head over to Desmos to confirm that this does in fact match with what we have. If we graph the function -2 times x plus 1 squared times x minus 2, we can see that it does go off to positive infinity as we head to the left. We can see that it comes down and intersects the axes at -1, 0, only to turn back and increase. It crosses the y-axis at 0, 4, keeps heading up, has another turning point before working its way back down to the 0, 2, 0, only to cross through the x-axis and then head off to -infinity as x goes all the way to the right. Now there's still a lot more to discuss about polynomials in general, but having the ability to get a sense of what they look like, a graph of them, a way to visualize the relationships between the inputs x and the outputs y, or f of x, is going to help us along the way to get a better sense of understanding these functions in general. I hope you found this helpful so far, and I hope you're looking forward to exploring some more of the details in future videos. As always, don't hesitate to let me know if you do have any questions, and otherwise, I hope you have a great rest of your day.